Okay, welcome to another video. It's going to be again 25 to 30-minute video on software-defined networking. The agenda for this video is I'm going to talk about how SDN evolved from the old networking architecture. What are the shortcomings of traditional routing and how SDN addresses those shortcomings? And I'm going to talk about generalized routing. We already know about routing, how the packets are forwarded from source to destination, but how SDN enables generalized routing. So software-defined networking. There is a video which is relevant to the SDN today, lecture that we are going to talk about today. And this video is very highly recommended. It's a keynote talk by Professor Nick McEwen at Stanford University. He gave this talk at one of the conferences as a keynote talk, and it's highly recommended. If you get a chance to view this video, this video talks about the first phase or version 1 of SDN and version 2 of SDN, the early years of SDN and the later years. I'm going to touch upon those topics in today's video as well. So internet is a remarkable story. It has seen tremendous success in the last 20, 30 years. Everything, all the businesses, education, finances, everything, the way that we interact with each other has moved to the internet. And the core behind the internet was the layering architecture that we have been talking about throughout the course. The layered architecture all the way from physical data link layer, then the internet protocol, network layer, transport layer, and people could build applications on top of that. This enabled that without worrying about IP or TCP or link layer or even the physical layer, anyone should be able to write a networking application. What this resulted is that people were enabled to write applications to do networking, to write networking applications to solve their own problems. So this change was really remarkable, which enabled everyone to write these network applications. People wrote chat applications using which they can interact. They wrote social networking applications and so on and so forth. But if you think about it, this change is only at the edge of the network. I would write an application, a networked application, much like you would have done in network programming courses as programming assignments. So those applications are written at the end. The inside of the network remained very closed. Nobody knows how how do you write the code for this router, which is manufactured by Cisco. So all the hardware, all the software, all the control, everything is built by one single equipment provider. The equipment was really close. It's not that you will get a general purpose machine and write an application which could be written by anyone and you will run that application there. It's a very specialized kind of equipment inside the network. A firewall is very specialized, a router is very specialized, a cache is very specialized. So all of these specialized networking equipment were closed for penetration, for development by anybody else. It's only the manufacturers or vendors who build these applications. So networking industry remained very old-fashioned, where you have this custom hardware with lots and lots of gates, on top of which there is an operating system, which same vendor would write and will provide features. And these features would also be provided by the same networking vendors who are developing this hardware and writing the operating system. So it's very closed kind of an environment. There is no room for somebody else like myself to go and say that you have got this hardware, please take my operating system, network operating system that I have developed, and this provides this new functionality, and nobody is going to be able to work with that. Okay, so it's very vertically integrated mainframe kind of a mindset. So what is mainframe? Mainframe is the old fashioned computers. Let's quickly talk about those. And this is the best analogy to the evolution of SDN that we have, that in the old days, in 70s and 60s, we used to have these mainframe computers which got evolved to PC. So these mainframe computers would have, huge amount of hardware, specialized and operating system applications, all built by one vendor, such as IBM or HP or Sun Microsystems. But then in the later days, this got evolved. In 1980s, we saw the evolution from this architecture to a very open kind of an architecture, where the microprocessor would be developed by the likes of Intel and then later AMD and other companies. And these microprocessors would provide an open interface. You might have seen in the courses that there are interfaces using which you can use a microprocessor in an application that you develop, a hardware application, a hardware system that you would develop by using a microprocessor that is manufactured by some particular vendor. So an open interface is available using which somebody can write an operating system such as Windows, Linux, or Mac OS, and other embedded type of operating systems. And these operating systems will also provide an open interface on top of which you can write a bunch of applications, and anybody could write those applications. So very unlike the old 60s and 70s type of systems, in which IBM would provide one specific functionality using their hardware, their operating system, and their own implementation of the application. So you can see that this was a transformation from a vertically integrated, closed, proprietary kind of very small industry, very expensive as well, to something which was very inexpensive, a horizontal integration here with open interfaces. And this led to the way of rapid innovation, because people could develop their own operating system, people could develop their own applications to do whatever they wanted to do. And SDN value proposition is very similar to the evolution of these computing systems to an open kind of an interface. So if you look at an old architecture in the older days, when the routers were manufactured, you would have these specialized hardware, specialized control plane with specialized features. And when we say feature, so it could be a router, it could also be a firewall, it could be a NAT device, but all manufactured by one single vendor. They would have their own hardware with their own control plane or operating system, network operating system, with a specialized application, network application, for which this hardware would be customized, and this hardware would be sold to the customers. So just like the computing industry saw the revolution or evolution from mainframe computers to the personalized computers, similarly, the networking industry also saw from this old router kind of an architecture to an architecture which was open. So where you would have this merchant silicon, some reference design, some reference implementations available from the likes of Broadcom and other companies, and they would provide an open interface, and on those open interface, anyone would be able to write their own control plane or operating system, if you like, a network kind of control. They would be able to provide that with an open interface northbound. So there would be a southbound interface from the control plane to this merchant silicon or the hardware, and a northbound interface. And these APIs from the control plane in the south direction and in the north direction would be open to anyone. And you would be able to provide any kind of network functionality by using this kind of an architecture. Using this architecture enables people like yourself and myself to be able to write these networking function application. So you can see that this is still an evolution from vertically integrated, closed, proprietary kind of expensive equipment, and which evolved into very economical, open interface sort of an architecture, which paved way for very rapid innovation. And we have seen that innovation in the last 15, 20 years in the networking industry. So if we summarize the evolution to the SDN, let me just quickly recompare the mainframe to PC evolution with the old router to the new SDN kind of evolution. So if you compare the mainframe days to the old router pre-SDN kind of days, let's take a look at the mainframe days. If you look at that, the hardware was developed by one company, OS applications all by the same company, either IBM or Sun or HP. Similarly, in the older days, the old router architecture or the pre-SDN architecture, if you wanted to get a network firewall, a network router, a network address translator, the forwarding hardware, the control plane, specialized features was built by one single company such as Cisco or Juniper, and later on by these Chinese companies ZTE or Huawei. So you see the evolution in both of these industries, in the computing industry on the left and in the networking industry on the right. So in the computing industry, we got into the personal computer era in the 1980s with the availability of early microprocessors from the likes of Intel. And similarly, for the networking industry, we saw the evolution to SDN, which came up in, the people started talking about SDN in 2005, but it didn't come into the commercial landscape until several years later. So if you look at the personal computer era, the hardware was manufactured by companies like Intel and AMD, and operating system was provided by a different set of companies, or even the open source such as Linux, and Windows, Mac OS was provided by Microsoft and Apple. On top of which, people could write applications, and who would write those applications? Well, there is a gazillion of companies who would write these applications, and you would be able to write those applications. So everyone would be able to write these applications on the personal computers, and we have seen that happening. Similarly, if you look at the networking industry on the bottom right, SDN provided the evolution from the pre-SDN days or old router, old specialized networking feature days to a situation where the data plane hardware, the control plane or the network operating system, and the specialized network functions, they were all provided by a variety of different possible vendors at each of these stages. So one company would be specializing in developing the hardware for the networking industry. Another company would be specializing in developing the control planes or the network operating systems, and yet other companies would be writing these applications to provide these network functions. So you would have an app to do the VPN, an app to do the firewall, an app to do the net, and that app would be running, that application would be running on a control plane, network control plane, which is developed by some other company, which is running on a network hardware, which is developed by yet another set of companies. Okay. So these architectural changes in the networking industries through SDN, what did this bring? Several benefits. First of all, it allowed the separation of the control plane from the data plane. If you recall, the router provides the functionality of forwarding the packets from one interface to any other interface. And to do so, it has a table which is populated by using the control plane functionality where the routing protocols are run. So SDN allowed separating those out. So logically centralized control plane with much more flexibility was able. And in more recent years, we also realized that it has left the data plane hardware, just the forwarding hardware inside the router, and that can also be specialized by making these programmable protocol independent packet processors by using programming languages such as P4, which will be able to program the hardware which is actually used to forward the packets from one interface to another interface. And then in more recent years, we also see additional functionality in the telecom networks. So SDN provided the functionality to be used and provide flexibility in the very wide area, large scale telecom networks, large internet scale internet service providers, where tier 1 type of service providers, they make use of SDN for for controlling their controlling their data centers and whatnot. So before we talk more about SDN, the one of the first functionality that or earliest functionality that people realized with SDN was the separation of the control plane and the data plane. If we quickly recall what the control plane and data plane were, the control plane provided the mechanism to compute the routing tables, and these routing tables will be stored in the router, in every single router. And this routing table will be populated by using the routing protocols and routing algorithms, which are considered to be the part of the control plane. The time scale for the operation of the control plane operations are per network event. If nothing happens in the network, if the network is static, the control plane's job is done. Unless something changes, you don't need to change any of the routing tables. Okay, so the changes in the routing tables made by the control plane are on a time scale which are slower time scales, per network event type of time scales. A new router is added, a link is torn down, or something like that. In contrast, if you look at the data plane will be using the tables which are populated by the control plane to actually forward the packets. That's the job of the data plane. And this is inherently local to the hardware inside the router. So it only depends on the arriving packets. It does not do any control kind of functionality, just looks at the packet and consults the routing table and forwards the packet to the right destination. So the forwarding mechanism itself is part of the data plane, copying the packet from an incoming interface to an outgoing interface. And in this case, you can see that the time scales that we see are per packet kind of time scales. So per router control plane, as in the traditional router case, old-fashioned kind of networking, we have every router which will receive a packet which would have some value written in the packet header, probably an IP address of the destination. By matching the IP address of the destination, this router will be able to make a forwarding decision by consulting the table which is already stored in the router. Okay. So how are these tables populated? These tables are populated because we have control plane running also in each of the routers, and these tables will be populated by those control planes within each of the routers. These control planes within each of the router, they must work in congregation in the form of a routing algorithm, which could be a distance vector or link state kind of a routing algorithm. And using that distributed kind of algorithm, you would be able to populate these forwarding tables or routing tables. The control plane would be responsible for calculating these table entries and populating those table entries into the router. Okay. In contrast, if you look at the SDN control plane, once again at the bottom end, at the data plane, the job of the router is still forwarding the packets which are arriving, and look at the some field in the packet and forward those packets to the desired outgoing interface. Okay, but in this case, how the control plane looks like. The control plane in this case is a sort of a unified remote controller kind of a plane whose job is to compute the tables. Now the tables are computed by this one single logically centralized. It could physically be distributed, but logically it is a centralized remote controller which would be computing these tables. And once these tables are computed, and these tables will be installed into the individual routers. So instead of computing these tables independently at each of the router, by of course making use of routing functionality or routing algorithms or routing protocols, in this case, the remote controller, which is logically centralized, would be calculating all these tables. So you can argue that this remote controller has a unified view of the entire network, and it has much more flexibility to compute these tables to provide any kind of functionality. Okay, so this control plane in this case is logically centralized, which is used to populate the tables inside the data plane using the flow-based API. What is a flow-based API? So packets coming from a source and going to a destination, they make up a flow. We'll talk more about the flow in a little bit. So software-defined networking, what does a logically centralized control plane bring? It would bring easier network management, will avoid router misconfigurations. If one router is misbehaving in a network of 5,000 routers, then you won't be able to do much. However, if you have a logically centralized sort of a network, it would be much more protected, and will provide greater flexibility to route the traffic flows going from one source to any other destinations. We will see in a little bit how this happens. And also think about table-based forwarding as allowing programming the routers. If you look at the table, it's providing you some information using which you can forward a packet from an incoming interface to an outgoing interface. So it's sort of programming the router. If you change the entry in the table, the router will be reprogrammed and will send that packet, the matching packet, to some other interface. So you can think about the programming task to be easier when it is centralized rather than when it is distributed. So people who have taken the distributed systems course or will take a distributed system course will realize that programming in the distributed environment requires this additional consideration where you have these different pieces of software at different locations, and you need to coordinate between those two, much harder as compared to a centralized kind of a programming environment. So also software-defined networking, by separation of the control plane from the data plane, it provides the implementation which is open or non-proprietary, rather than Cisco providing that kind of a control plane functionality. Anyone else, 200 companies can come forward and provide this functionality. So now let's take a look at how SDN addresses some of the traditional routing issues. We might have talked about some of these traditional routing issues, but let's take a look at a couple of examples and see where the traditional routing fails and SDN might come to help. Okay, so traditional routing issues, first example is that, let's say you have this little toy network where this red kind of flow is going from this computer on the left to this computer on the right, and it is passing through a bunch of links and routers, as it normally happens in the case of the internet, that you have packets going from one source to a destination. Okay, so how this red path is computed, you can look at these link weights which are written in the picture. So all the way going from this router U to router Z, we are passing through a set of links which are providing the least cost path from left to the right, from router U to router Z. Okay, so what if the network operator wants the U to Z traffic to follow along this upper path, U, V, W, Z, instead of the shortest cost path, the least cost path, which is U, X, Y, Z. So instead of going from U, X, Y, Z, I want to go U, V, W, Z. You can certainly do that, but this will require you to play with the weights of the links. Okay, so you will need to redefine some of the link weights so that the traffic routing algorithm computes this path, the red path currently shown, U, V, W, Z. This becomes the shortest or least cost path. In order to make this a least cost path, you will need to adjust the link weights. Okay, so you can certainly do that, but the only knob that you have available is the link weights. There is not much control. I cannot do much about it. If you have lots and lots of flows going in, it would be much harder or maybe even impossible to be able to adjust the link weights to come up with a desired set of flows going from some set of sources to set of destinations. Okay, so let's take a look at another example which traditional routing will not be able to solve. In this case, what if the network operator wants the traffic from U to Z be split for the load balancing purposes? So if there is too much traffic which cannot be passed through one single path, I would like to divide this traffic onto two paths. Okay, and can I divide this traffic onto two paths? So when some packets arrive at U, some of those go to V and some of those go to X, although all of them have the same destination IP address. And you will appreciate that the traditional routing will not allow that, because when the packets arrive at you, if they have the destination IP address, the table at U will be consulted and the destination IP address will be matched. You will find only one interface where you will send these packets to. So you will not be able to do this kind of a load balancing unless you come up with some new kind of a routing algorithm, okay, which might also be very cumbersome to find. Let's consider one more example. So what happens if you have these two flows, the red flow and the blue flow, which are as shown? What if this router W, which receives packets for the red flow and the blue flow, wants to send the red packets along this upper path and the blue packets to Z through Y? Okay, can we do that? This traditional routing will still not allow this. And once again, the reason for that is it's destination IP based forwarding. We will not be able to provide that. However, SDN, which enables generalized forwarding, can be used in this case to achieve any kind of desirable routing. We should be able to address all these three examples where traditional routing has issues. We will be able to use generalized forwarding and SDN to achieve this routing. So what is generalized forwarding? So generalized forwarding is basically you still are forwarding packets from one interface to another interface. You will still have values written inside the packets and they will be forwarded by matching into a table. And taking some action, and that action would be forward. So if you look at the traditional destination based forwarding, that's also a match plus action, a specific example of match plus action. What you do is you match the destination IP address, and the action you take is whatever outgoing interface the table tells you, you take the action of forwarding the packet onto that interface. So the traditional routing is a specialized case of generalized forwarding. What else generalized forwarding might be achieving in this case? So in the case of generalized forwarding, you will have this match plus action, and the match doesn't necessarily have to be based on just the destination IP address. And the action also is not necessarily just limited to forwarding the packet to an outgoing interface. So match can be very generalized, and the action can also be very, very generalized. Okay, so if you look at that traditional old-fashioned destination-based forwarding, you forward based on the destination IP address. You match the destination IP address, and your action is to forward it to one outgoing interface. In the case of generalized forwarding, many header fields can determine the action. So remember, every packet will have not just the IP address of the destination, but also will have the IP address of the source. Will also have the port numbers. Will also have the, if it's a link layer packet, then it will also have the link layer addresses, the MAC addresses. That you can also do the forwarding based on any of that information, and many different actions are possible. So one action could be drop the packet. The other action could be copy the packet, or modify the packet, or log the packet, or maybe forward the packet. So lots and lots of different actions are possible in this case as well. Okay. So let's take a look at this flow table abstraction. You have this flow table where you will be matching with something and you will be taking an action. Okay, so router's flow table defines the router's match plus action rules. Just like in the case of old-fashioned routers, the routing table also defines the match and action. The match is the destination IP address and the action is forward to an interface. Okay, so in this case, we define a flow by the header values in the link layer header or the network layer header or the transport layer header. And the generalized forwarding has the simple packet handling rules. What should be done with the packet? Should you forward the packet? Should you drop the packet? And so on and so forth. Now, you might be able to realize at this point in time that if your action is generalized, so if your action says that instead of forwarding, you just drop the packet, maybe you can achieve the firewall functionality. Firewall does the same thing, that if you see the packet coming in from an undesirable source or destination, then you drop that packet. So you can take this generalized action on a packet to realize the firewall functionality. So match could be the pattern of values in the packet headers, not just the destination IP address, which is one example of the match pattern. There could be other match patterns as well. And the action could be drop, forward, modify, match packet, or even send the match packet to the SDN controller, which is your control plane. You can also do other functionalities such as priority and also count the packets in order to do some statistics on the how many packets have been sent from this source to this destination on a specific port. Okay, so if you look at these tables are slightly different from, or more generalized from the regular routing tables that we have been seeing all along. It has entries which has match and the actions. So for example, in the first entry, the match is if you see the packet coming from any source and the destination is 3.4. You forward it to. So this is the action on the right hand side. You can see that there are other entries where you can do source-based forwarding if the source is 1.2. And destination is anything, then drop the packet, which means anything which is coming from 1.2 kind of an IP address. This is something which I'm going to firewall. I'm not going to allow that traffic. I will just drop that traffic, and so on and so forth. Okay, so OpenFlow is basically the protocol which provides this functionality where the separated data plane and the separate control plane, they can talk to each other. So OpenFlow flow table entries uses this match, action, and stats kind of rules. So match could be on any of the things. What are the header fields that we can match on? So some of the network layer headers, remember in the original old-fashioned kind of routing, we only look at the destination IP address. But now I have the source IP address or IP protocol type, IP type of service that I can use for doing the matching. I can also do the matching based on the transport layer headers. So port numbers can be used as the match criteria. And similarly, the link layer headers can also be used for the match criteria. Once the matching is done on specific criteria, then you take an action. In the old-fashioned sort of routing, the only action that you had was to forward the packet to the ports. Or maybe if the TTL is expired, then you will drop that packet. But generally, you will only forward the packet to one of the interfaces, outgoing interfaces or ports. But in the case of OpenFlow or SDN, OpenFlow, which is the protocol used in SDN for communication between the controller and the data plane, then additional actions that you can take is drop the packets or modify the fields in the header or encapsulate and forward to the controller. And then you can also take some stats. So OpenFlow has this pipeline of matching, taking some action, and then collecting the stats. Okay. Some examples of OpenFlow. If you want to do the standard destination-based forwarding, which is done in the old-fashioned routers, all you need to do is that put star in all of these fields except for the destination IP address. So what this will do is that it will match the destination IP address 51608, and the action is to forward it to port 6. A traditional router would also do that, match the IP address and forward it to an outgoing interface or outgoing port. Okay. Now, if you want to implement a firewall kind of a functionality, then what you want to do here is you want to block the traffic from some undesirable, sent to some undesirable ports. Okay. So in this particular case, in this particular example, if the destination port is 22, TCP destination port is 22, no matter what the rest of the fields are, where the packet is coming from, which IP address the packet is going to, if the destination TCP port is 22, the action is to drop this packet. Another example of firewall is if you want the source IP address 128.119.1.1 to be blacklisted. If you want to blacklist this IP address, then any traffic coming from this source IP address, if the source matches this, no matter what the other fields are, this packet will be dropped. Similarly, you can also do layer 2 type destination-based forwarding. So instead of looking at the destination IP address, I'm going to look at the destination MAC address, which is also part of the packet. It's in the link layer header. So layer 2 frames with destination MAC address, which is given by this, they will be forwarding to the outgoing port number 3, outgoing interface number 3. Okay, so you can see that by using SDN and specifically OpenFlow, you are able to provide any of these kind of functionalities. So this provides you an abstracted way of doing these match plus action, which unifies different kinds of network functionality that you want to provide. So for example, if you want to build an standard layer 3 kind of a switch, which we call a router, that we have been seeing all along, which does destination IP-based forwarding. So in this case, the match is the longest destination IP prefix, and the action is forward to an outgoing link or outgoing interface. Okay, this is what our standard router will do, and this is what we will do in SDN as well. So we can use SDN to make a device look like a router. I can also use SDN to make a device look like a layer 2 switch. If I want to make a device look like a layer 2 switch, then the match in this case should be on the destination MAC address rather than the longest prefix IP match. In this case, the action would be forward or flood. Similarly, if I want to build firewall kind of functionality, the match would be the IP address or port number or a combination of these two, and the action would be to permit or deny this traffic. If I want to build this network address translation kind of functionality, the match would be an interior IP address or the port number, and the action would be to rewrite the IP address, much like the network address translator would do, and the port number. Okay, if you think about it, unlike old days, this single device can be programmed to be any of these devices. I don't need to buy different kind of specialized hardware, specialized boxes to do router, layer 2 switch, firewall, or NAT, or cache, or other kind of functionalities. The one single device, I can program it to be a layer 3 switch or router, or a layer 2 switch, or a firewall, or a NAT, just by modifying the match and action rules. Okay, so one last example on OpenFlow is orchestrated tables can be created to give you a network wide behavior. So for example, in this particular example, a network is shown. I want the datagrams or IP packets from host H5, which is here, and host H6, which is here, should be sent to H3 or H4, and H3 and H4 are here on the bottom right. So I want to send traffic from top left H5 or H6 to bottom right to H3 and H4. Normally this traffic would come from this switch S3 to S2, or S3 to S1 and S2. If I want to force that behavior, if I want to force this behavior, I can use OpenFlow. In these three switches. Otherwise, it will do the default kind of routing. Okay, so what would be the table entries look like? The table entries in this case would look like that. What is the match action kind of a table in switch S3? The match is that if you are coming from 10.3.star, which means any of these host 5 or host 6, then forward that to interface number 3, which is this interface number 3. So the packet will come here. Once the packets will come here, then I should have a table at S1 as well. And that match action table will say that if you receive a packet which is coming from interface number 1, ingress port is 1, incoming interface is 1, and the source is 10.3.star or 10.2.star, then take that packet and forward it to outgoing interface number 4, and this outgoing interface number 4 will lead the packet to S2, whose table is shown here, which will make sure that the packet reaches to the correct destination. If the ingress port, incoming port is 2, and the destination is 10.203, which is host H3, then it will be forwarded to port number 3 or interface number 3. And if the match is for 10.204, which is the IP address of host H4, then it would be forwarded to interface number 4. This is the interface number 4. So summarizing, software-defined networking has provided us some very interesting functionality. One is the generalized flow-based forwarding. Instead of having those IP address, destination IP address based routing tables, we have these generalized tables, flow tables, which can be populated by using OpenFlow or an alternate. Okay, there is a separation of the control plane and data plane, and the control plane is external to these data plane switches. I don't have to put the control plane functionality inside the same router box that used to happen in the old times of networking industry. And what this does is that this allows you to have programmable control applications, routing, access control, all of these new kind of network functionality that we can think of. I can provide those functionality by writing an application for that. Okay, so we divide this SDN architecture into these three stages. One is at the bottom end, we have these data plane switches, much like the regular switches. They will have these tables, but instead of the routing tables, they will have these flow tables. These are SDN controlled switches, and these switches will be controlled by the SDN controller through this southbound API, this southbound interface of the SDN controller, which is an interface, programmable interface, using which this SDN controller will be talking to the SDN controlled switches. Okay. And similarly, this SDN controller will be talking to these network control applications. These are the applications which are the brains of network control. Any new kind of network functionality that I want to implement, I can implement it. And that functionality will be able to talk to the SDN controller by using the northbound API of the SDN controller. Okay. So this finishes the discussion on SDN. And I will stop here.